Hi students, welcome to the video module on crystal defects part 2. This module refers to the second type of imperfection, that is line imperfection, which is also known as dislocations. So before going to study about line imperfection, I recommend all of you to have a basic idea regarding crystals, crystallography and related things, and also the previously uh, discussed a module on point defects. So all these videos are available on these links. So I recommend all of you to watch these videos before studying about line imperfections or dislocations. So these 4 videos refers to crystals and crystallography, X-ray diffraction technique, and the fourth one is about point defects. Okay, so now we can move in detail about crystal defects. Crystal imperfections are classified into 4 groups. As you can see here, that belongs to zero-dimensional or point imperfections, one-dimensional or line imperfections, then surface imperfections, and volume imperfections. About point imperfections, that is again classified into 3: vacancy, substitutional, and interstitial. Line imperfections or dislocations are classified into edge dislocation and screw dislocation. Surface imperfections are a free surface, grain boundary, twin boundary, and stocking fault. Volume imperfections are void, crack, inclusion, and precipitate. We'll learn about these in detail. In this video module, we are going to learn about one type of a main crystal defect, that is line imperfection or dislocations. Line imperfections are one-dimensional imperfections in the geometrical sense, and they are mainly dislocations or line imperfections are mainly classified into 2 types. One is known as edge dislocation, and the second one is known as a screw dislocation. So there are 2 types of dislocation. That is, first one is edge dislocation, and the other one is screw dislocation. So we will detail these 2 types of dislocation in detail. Now we will learn about edge dislocation in detail. You can see an arrangement of a perfect crystal here. It's an arrangement of a perfect crystal. It's made up of vertical planes parallel to one another. See, one plane, 2, 3, such a number of vertical planes stacked parallel to each other. If one of these vertical planes does not extend from top to bottom of the crystal, but ends part way within the crystal, as you can see here. See, this plane, it is not completely extending from top to bottom, but it ends almost part way from the top. So you can see that there is a type of distortion in the crystal due to this type of an arrangement. So if you consider the crystal as parallel planes, there may be a plane that extend from top to somewhere in between, not completely. So there is a difference, or we can consider this like a missing half plane, or we can consider it as an extra half plane. Actually, it is not like that anyway. But you see, the equilibrium, when you consider the top portions of that, there is no change in the equilibrium state. When you consider the bottom portion like this, there is no change in equilibrium. You can see here also. That is in equilibrium. And you can consider here that is also in another sort of equilibrium. Only the problem occurs is at the end of that what we call as the extra plane. So it is like this. That plane extends backward like this. Okay. So it is like I'm just drawing. This is that particular plane that extend only to halfway. And this is the complete crystal. Okay. So this line or here is the dislocation occurs. We call it as the edge dislocation. See, it is represented in this way. This is that plane, and here is the dislocation. The dislocation is not over the complete surface. It is over a line that at the end of that plane that is terminating in between somewhere. Okay, so you can see in this picture also. So yeah, this is one such plane. Okay, so this can draw backward like this. See, this is that plane. So that line, the line here, we call this line. This is the this along this line the dislocation occurs. So this is a line dislocation, a line imperfection. Line imperfections, or edge dislocations are symbolically we can represent this either like this or you can like in this way, in the reverse also. So the first one we call it as a positive edge dislocation, and this one we call it as negative edge dislocation. Now we can look into the edge dislocation in another way also. Let us see that. See, this is the same arrangement, the same edge dislocated crystal is drawn here. Okay, you can see a shaded region A, B, F, E. It is part of the plane marked A, B, C, D, A, the full plane A, B, C, D, and in that we can see a plane A, B, F, E. Now, this plane ABE, the crystal over ABEFE, if there is a missing plane there, you can consider like this particular plane is moved or displaced due to edge dislocation or the line imperfection. You can consider that the plane in this region, you can see the plane in this region is in alignment with one of the plane here. It is slightly shifted. There is no such shifting in this region. The shifting occur only from the line EF and to the right side. This plane ABCD, the full plane ABCD, is called the slip plane. We call this as the slip plane. The region ABEFE over which the displacement is done is called the slipped part of the slip plane, and the region EFCD over which displacement is not done is called the unslipped part of the slip plane. So the slip plane can be divided into two. One is a slip portion ABEF or ABFE, and the unslipped portion EFCD or CDEF. I mean, the boundary between the slipped portion and unslipped portion. In this figure, it is EF. Is the dislocation line. EF is the dislocation line. Now, the magnitude and direction of this displacement are defined by a vector called Burger's vector. It is normally represented by BV. Burger's vector characterizes the dislocation line. Now, how to find the Burger's vector? So for finding the Burger's vector, first we have to draw the Burger's circuit. How to do that? See, here is a perfect crystal arrangement. So in that, I am starting from the point P, upward by 5 units. Then I am moving to the right by 5 units. No, on the upward direction it is 4 unit I am moving, because from the middle of one crystal. Okay, just 4, whatever it is, just it's 4 unit I am moving upward, and 5 unit in the right direction. Again back 4 units downward, and again 5 units. Now we reach back to the point P, and what we traced now is known as the Burger's circuit. Now let us try to draw the Burger circuit for an edge dislocated crystal shown in figure B here. Starting from the point P, here is the point P. We are moving 4 crystal distance upward, so 4 moved upward. Then we move 5 distance in the right direction. Then again downward 4 direction, 4 crystal distances. Then again 5 distance to the left, crystal distance 5, and we reached back to a point Q. We not exactly reached back the point P. Instead, we reached another point Q. So here, a vector directing from Q to P, we call this vector between Q and P as the Burger vector, the Burger's vector. Here the Burger's vector is BV, that is equal to vector QP, and that is represented by B. Vector B is used for that. And you know, the Burger's vector is always perpendicular to the edge dislocation line. In this picture, which one is the edge dislocation line? It is a line, see the red dot there, from there inward, that is the, or you can draw, this is in the blue color diagram I am drawing, that is a line, right? And the Burger vector we draw in the downward, that is like this we got, right? So the Burger vector is always perpendicular to the direction of edge dislocation line. While drawing the Burger's circuit, we can draw this clockwise. The Burger circuit we completed here in the clockwise sense. The direction of Burger's vector depends on the direction of the circuit, which can be clockwise or counterclockwise. To avoid this confusion, you can see a unit vector T. A unit vector is assigned to denote the direction of dislocation line. Here the dislocation line is like this. the red line that I'm drawing. This is the dislocation line. Oh, okay. So a unit vector t is assigned in that direction. Now apply RHS right hand screw rule convention here. Just keep the tip of the screw at this point of interest and turn it clockwise. If the screw also tends to move in the plane of the paper, the above vector t is into the plane of the paper. So on rotating the screw to the right hand side, it moves along the direction of this vector. Then the Burger's vector also has to be drawn in the clockwise direction. That is the convention that we generally use. So draw a vector, unit vector along the direction of dislocation line. Use right hand screw rule. So in order to move the screw in the direction of this vector t, if we move that in the clockwise sense, while moving the screw in the clockwise sense, if the tip of the screw point in the direction of the vector t, then the Burger vector also has to draw in the clockwise sense. Next, we are going to learn about another type of line imperfection that is known as a screw dislocation. Let us see what is meant by screw dislocation. Here you consider this shaded region A, E, F, D. That shaded region is slipped to the left. I hope you remember in the previous case of edge dislocation, that shaded region is slipped towards the unslipped plane. Here A, E, F, D and E, F, C, B. There are two. We divide the full slip plane in full plane into slip and unslipped parts here. So in the case of edge dislocation, this slip plane is moved towards the unslipped part. But in a screw dislocation, this slip plane AEFT move towards the left. In this particular case, it is moved towards the left. You can see in the next picture here. The first one is a perfect crystal arrangement, and the next one is a slipped part. See, the plane AEFD is slipped along the dislocation line. See the dislocation line EF. In the previous case of edge dislocation, the slipped plane moved towards the dislocation line. Here it is moved along the dislocation line. And you see the vector T. As usual, the vector T is along the dislocation line. T vector is drawn along the dislocation line. So this type of a dislocation is normally known as a screw dislocation. Now let us see how to draw the Burger's circuit and Burger's vector here. So as we discussed the Burger's, to draw the Burger circuit, just imagine we keep a screw here. This is a right hand screw pointing towards. So on rotating that screw in the clockwise sense, like this is a clockwise sense. If the tip of the screw is moving along the T vector, then the Burger circuit has to be drawn in the clockwise sense. So for moving the screw tip along T vector, or in the other way, if you are rotating the screw in the clockwise sense, then the tip of the screw move opposite direction to the T vector, then the Burger's vector has to draw opposite of right hand, I mean opposite of clockwise, that is counterclockwise. Once again, keep the tip of a right hand screw at the start of line dislocation and rotate the screw clockwise. If the tip of the screw is moving along the direction of T vector, then the Burger's vector has to draw in the clockwise sense. If the tip of the screw is moving opposite to the T vector, then the Burger's vector has to draw in the counterclockwise direction. Here you can see when you rotate the right hand screw in the clockwise direction, the tip will move along the t vector. This is the t vector direction. So we have to draw the Burgers vector in the clockwise end. So I'm starting the Burgers vector from the point, just let's see the point P here. So then go in this way, this way, this way, this way. It will reach here. So how much we moved? We moved 1, 2 distance here, 1, 2, 3 here, 1, 2, 3, 4 downward, then 3, then here totally we know in the downward it was 4, upward we already moved 2, now 2 more, so that totally 4 here on the both sides, but we are not reached at the starting point. There is some distance, so you can see the vector. So it is like this: we started from here, moved 2, then we moved 3 distance here, then that is an example. We moved 4 here, then we moved 3 here, then we moved 2 here. I reached like this now. So this was the starting point P, and this was the end point Q. Now draw a vector from Q to P. This is the Burger vector. Okay, you got the point. So this is the way to draw the Burger circuit and Burger vector. Now you see here in this case the Burger's vector B is parallel to the T vector, the line dislocation line unit vector T. The Burgers vector P is parallel to the vector T in this case. But in the case of edge dislocation, the Burgers vector was perpendicular to the T vector. There is a difference between these two. If you turn the screw through one full rotation, we move the screw backward or forward distance equal to the pitch. This feature has led to the name screw dislocation. That means if you rotate the screw completely, it will move along the dislocation is actually along the Burgers vector. So that is why it is like moving the screw. It's a screw that is when you completely rotate the screw once, either backward or forward, it move a distance equal to the pitch that will be equal to the Burgers vector here. So the displacement or the dislocation is like along the screw, along the rotation of the screw. It is not same in the case of edge dislocation. So here the dislocation is along the screw moving the tip of the screw moving direction. So that is why the name screw dislocation appear here. Here also positive and negative screw dislocations here. And you can compare this as a spiral staircase whose central pillar is coincide with the dislocation line. It is like this, right? A spiral. It's like a spiral staircase. The screw dislocations are symbolically represented in two ways. One is this is one direction, one, and the other one in the opposite counterclockwise. Depending whether the Burgers vector is parallel. So here the Burgers vector B is parallel to T. In the other case, Burgers vector is anti-parallel to T. So first one is called a positive, and the next one is called a negative type of screw dislocations. Now, let us see a total picture of line imperfections. Actually, any general line imperfection or dislocation line is a combination of edge and screw types. So you can see the shaded region or the hatched area in this crystal. This is a perfect crystal on the first side here. And you imagine removing or a plane is missing in that one, so that plane moved to the, you can see the next picture. In that you can see there is a combination of edge dislocation and screw dislocation. See, it is actually like a curve. See, this is a curve type. That means here the bottom portion of this area, it is moved inward. So there is an edge dislocation. And when you look into this from the right face, it is like a screw dislocation. When you look into this from this front face, it is an edge dislocation. So this dislocation is actually a combination of both the type of dislocation. And actually it is like a curve inside that, which is the T vector. So the Berger vector here for the edge dislocation, the Berger vector is shown in this direction, right direction, and in the case of from the right side, it is screw dislocation, and the Berger vector is this. See here, both are in the same direction. You can see both these are in the same direction. Okay, the T vector goes into the plane of the paper on the front face. This is about B vector. Now look at the T vector. This is the T vector. It starts from here. Okay, there's an edge dislocation. The T vector is along the line, and you can see the dislocation line, or the edge dislocation line changes like this. It comes, yeah, like this. See, it goes into the plane at one phase, and it comes out of the plane on the other phase, like this. This is the T vector. And if you draw the right hand screw rule there, for getting this direction, you have to move the screw in the counterclockwise direction. That is why the Berger circuit there we drawn in the form of in the counterclockwise sense. Okay, so it starts here and it ends here. So that is why the Berger vector is in this direction for the screw dislocation, and here the edge dislocation vector. Okay. So thus the Berger vector B has the same magnitude and direction in both these cases. The magnitude is same and its direction is also same. So thus we obtain an important result that Berger vector is invariant. That is, it has the same direction and magnitude all along a dislocation line, irrespective of the character of the dislocation, whether it is edge dislocation or screw dislocation. Okay. Now let's see shaded region or hatched area of the slip plane enclosed by an elliptical loop like this. The previous we shown a part of that is a curve only. Here you see the edge dislocation in the form of a loop. A dislocation or hatched area, the slip plane, I mean, in the form of a loop here. So this we can consider the combination like of, you see here a positive edge dislocation. In the previous case, actually, we considered this much only. Look, see, in the previous slide, we are shown like this only, this much only. The T vector emerges out. But you consider that is the curve is completely inside the crystal. Now, like this. That is what here. So it is a combination of this. There is a edge dislocation. This is positive edge. Then there is a right hand screw here. Then there is a negative edge. Then there is a I mean, this is a positive screw and this is a negative screw. It's a combination of that. Everything will be there if the loop is inside the crystal. So in between these points, the dislocation has a mixed character. That means here it is completely edge. Here it is completely screw. Here it is completely edge. Here it is completely screw. And in between, it is a mixed character. In the previous case, we noticed only one. The front face was the edge and the side face was the screw. In between, that is actually a combination of both the type. Here the Berger's vector can be resolved into two directions, parallel and perpendicular to the line, and thereby define the screw and edge components of the combination here. You know, dislocation have a certain geometrical characteristics. The vector sum of Berger's vector of dislocations meeting at a point, that point is called a node, it must be 0. Okay, the vector sum of Burger's vector of dislocations meeting at a point. So if you consider any point where the dislocation meeting occurs, there we take the sum of Burger's vector, that will be 0. It is analogous to the Kirchhoff law of electrical current. The currents coming towards junction must be going out like that. If this is a point, whatever the Burger vector coming here and the Burger vector going out from that position. So the vector sum of Burger's vector at a meeting point of dislocation, which is called a node, is 0. And the t vectors of all the dislocations meeting at a node must either point towards it or away from it. See, in case, this case, this is the t vector. It is towards it. And here you can see this is a t vector. It is away from it. Okay. So the t vectors of all dislocations meeting at a node must be either point towards that node or away from the node. A dislocation line cannot end abruptly within the crystal. So dislocation line will not end at any point. Either it ends at a node or at the surface. The dislocation line may end at the surface. If here the surface, it ends there. Otherwise, it will end at a node. Okay. Okay. Till now we discussed about screw dislocation and edge dislocation and some of their properties. Now we'll continue with some more properties of dislocations. We learned that dislocation have distortional energy associated with them because in the case of edge dislocation, you can see that the arrangement or the interatomic separation will be distorted so that there will be a compressional strain or an elongational strain. Whether see, so at this region there will be a compression, and so this is one type of edge dislocation. So that produces a compressional strain there. If we are considering about screw dislocation, it produces a shear strain along the dislocation line. Whatever it is, there is an elastic strain associated with the dislocations. So the elastic strain energy per unit length, E, the elastic strain energy per unit length of a dislocation of Burger's vector B is given by E equal to, or E is approximately equal to mu B square by 2, where mu is the elastic modulus of the crystal. Now let us try to do a problem to find the elastic line energy. Compute the line energy of dislocation in BCC, the body-centered cubic structure of iron. The Burger vector is given as half of 111 direction. This is 111 direction type. So the dislocation Burger's vector B value is 1/2 of 111 direction vector. The shear modulus of iron is 80.2 giganewton. So how to calculate this? The lattice parameter of BCC structure of iron is A equal to 2.87 angstrom that we obtained from the standard value tables, 2.87 angstrom. Now you have to find how much is the length of 111 plane. 111 plane is the line shown here in this diagram, the red color line shown here in the diagram. That is 111, one along x and y and z axis. So 111 direction. So how to find the length of that? If one side is A, Then this side also a. This will be, what will be that? It will be a square plus a square. That is 2a square under root. It is root 2a. So now this is a. So now this is root 2a and this is a. So what will be the red color diagonal? That is root 2a whole square plus a square. That will be 2a square plus a square under root. So it will be 3a square. It will be root 3a. Okay. So that is why here the Burger vector is half of root 3a. So half of root 3 times, what's the a value? 2.87, 10 to the power minus 10. That is why 2.49 angstrom, 2.49, 10 to the power minus 10. Now the value of E calculation. What is E? Is equal to mu b square divided by 2. Mu is 8.2, 10 to the power 9. B is 2.49 square, 10 to the power minus 2 square is 10 to the minus 20 divided by 2. That gives 2.49, 10 to the power minus 9 joule per meter. In real practice, dislocation in a crystal can be classified either as full dislocation or partial dislocation. For a partial dislocation, the Burger's vector is a fraction of lattice translation. For a full dislocation, the Burger's vector is an integral multiple of the lattice translation. We are mainly dealing with full dislocation here. We know that the elastic strain energy is proportional to square of the Burger's vector. Just now we learned that E is equal to mu 0 b square divided by 2. So elastic strain energy is proportional to square of Burger's vector. So in order to reduce this strain energy, dislocation tends to have as small a Burger's vector as possible. So the dislocation tries to occupy, or they need to reduce the strain energy. So for that, the Burger's vector as smaller as possible. So how this possible? Consider an example of an edge dislocation in a simple cubic crystal with a translation vector b. So if two incomplete planes together occurs on a slip plane, then the Burger vector will be twice the translation vector. So 2b. Here b is not the Burger vector. Here we are considering b as the lattice translation vector. Okay. Then the two incomplete planes to be together on the slip plane, so that the Burger vector of this dislocation is 2b. But the two planes will have a tendency to break up as to separate planes, so that to reduce the Burger's vector into b in each case, so that 2b dislocation changes to two separate planes, and then therefore the Burger's vector will be b and b. Therefore the energy changes to before breakup of this, the energy was mu 0 times 2b square divided by 2. Equation is mu 0, or mu, I mean mu times b square divided by 2. B is the Burger vector. Here that b value is actually, it is better, or okay, b value is 2b here. So mu times 2b whole square divided by 2 was the energy earlier. But when they separate into two with translation vector b, then the Burger vectors also b for that. Therefore, the energy will become mu 0 b square by 2 and mu 0 b square by 2. Two separate. So that the energy of each plane will be 50%. Instead of considering them separate as a single entity, they break up into two. with energy, elastic energy decreases to 50% of the initial value. So in general, a dislocation with the Burgers vector B1 will tend to dissociate into two, B2 and B3. So B1 square will be less than B2 square plus B3 square. I mean, B1 square will be greater, with considering the other. So it reduces, the Burger vectors reduces, the elastic energy also reduces. The Burgers vector in ionic crystal possess slightly higher value compared to the other crystals. For example, the Burgers vector in cesium chloride, it cannot be half of 111 direction. It can be a full translation vector 100 direction. If we have an edge dislocation with a Burgers vector half of 111 in a cesium chloride crystal, the extra plane will have extra electrical charges. The crystal as a whole has to be electrically neutral, so that charge neutrality will be eliminated. So ionic crystals, if there is an extra half plane of atoms contained only atoms of one type, then the charge neutrality condition would be violated. So that is an unstable condition. So that is why these examples are selected here. Cesium chloride, if we take 111, half of 111 direction, that will make the charge neutrality to lose. And the same way, case of sodium chloride also, we cannot select half of 100. 100 means an edge, from one corner to half of the edge. That is half of 100. 100 means it's NaCl crystal. This is a cubic crystal. One edge of NaCl crystal is 100. So if we take half of that, means we are then there will be an extra charge will be there. That is not a stable situation, because as a whole, as electrically, the crystal has to be neutral. Okay. So some type of planes are only possible in this type of ionic crystals. So this restriction in ionic crystal tend to make the Burger vector large. What restriction is that? The restriction is that dislocation cannot introduce any extra charges in that, or charge neutrality has to be maintained. So this is a restriction in ionic crystal tend to make the Burgers vector large. So for example, in the FCC crystal of copper, the Burgers vector, you can see the copper, the Burgers vector is 2.55. But in case of sodium chloride, it is larger than that. Sodium chloride is an ionic crystal. It has got 3.95 angstrom. A dislocation already present in a crystal can be made to move by applying an external stress. The motion of a dislocation on a plane that contains the direction vector t and the Burgers vector b is called the glide motion, which is the vector that consists of the direction vector and the Burgers vector b. It's along the slip plane. So the motion of edge dislocation, you can consider the moment of edge dislocation here. So you can see the dislocation is here. This line inverts into the plane of the board. So by applying a tension in this direction, you can make this dislocation, the line dislocation, now it's here, and the next stage it reaches here. So the dislocation moves. So here, which is the plane that consists, so here you can see the plane. So it moves along the plane. Such a motion of a dislocation on a plane that contains the vector t and the Burgers vector b is called glide motion. And we know that there is only one plane that contains both b, the Burgers vector b, and the direction vector t when they're not parallel. The glide plane is uniquely defined for a pure edge dislocation as well as for mixed dislocation. Now, let us see another type of dislocation. So here what we learned is glide motion. Glide motion is on applying an externally applied tension, stress, the edge dislocation plane can move from one edge to another. Now, in the next type of motion, that is called climb motion. The motion of an edge dislocation on a plane perpendicular to the glide plane is called the climb motion. You can see here in this picture, this one is the glide plane here, the full plane. This is the plane shown there, and this is the extra plane which is not present here. Due to that, there occurred an edge dislocation along this line. In the previous case, we applied a tension in this direction so that this plane moved to another side. But now what we are going to do is, what will happen if we insert a layer of an extra layer of atom into this? Then this layer will come down to this position, right? It is climbed down in that case. The motion of an edge dislocation on a plane perpendicular to the glide plane. So here we know the glide, this is the glide plane. So the motion of edge dislocation, this is the edge dislocation. It is moving either up or down. That means it is moving perpendicular to the glide plane. How it moves down? By inserting a layer of atoms. Now think about removing a layer of atom from that. Now what will happen? The plane will move up. It is climbing up. So this type of a motion is called a climb motion. The previous one was glide motion. So you can introduce a climb motion by either by adding rows. So adding rows will make the layer to move down, and or by subtracting rows. Subtracting rows will make the plane to move up. And climb motion is non-conservative because there is an addition of atomic layer or removal of atomic layer. Therefore, it is a non-conservative type of motion. During climbing up, the incomplete plane shrinks because it reduces the number of atoms. Atoms move away from this. During climbing down, the incomplete plane extends, right? Because one layer is added, so the incomplete plane extends. Okay, that is climbing up and climbing down type of motion. In the case of screw dislocation, we know that there is no unique glide plane for a screw dislocation. So it can change the slip plane during its motion. So you can see in this figure, there is you can see two slip planes here, slip plane 1 and slip plane 2. Okay, so as the slip plane, we can see it is moving in this direction, and the other slip plane, it may move like this. So what happens? Cross slip occurs. Due to this type of a motion, cross slip, or one slip, one particular plane cross slip into the other plane, and they continue to glide over the surface. So this illustrates how cross slip of a screw dislocation. As the glide plane is uniquely defined for an edge or a mixed dislocation, they cannot cross slip. But only in the case of screw dislocation, this type of cross slip occurs. Okay. Okay, students. So we learned about line dislocation and their properties. Thank you, students.